Hi, Josefa. Good morning.
Hi, Yanni. How are you?
Good.
Hi, Ying. Hi, Dima.
Hello.
Hi, everyone.
Hello.
Hi, Rita.
Hey, hi. Hi. Hi, Sophia. How are you?
Hello, good morning. Good, how are you?
Good, good. Thank you for joining.
Of course, looking forward to this.
Yeah, likewise. Yeah, we'll wait a couple minutes. We usually get around 30 to 40 people, so we'll see what's going on today.
That's great.
I think it's a lot of the architecture subgroup.
That's wonderful. That's a target audience. Like your big ILLIXR box on your whiteboard or on your wall.
Yeah. Actually, That's all from pre-COVID. And so
Oh.
2 years, I did not, almost I didn't come in, and now it's so hard to wipe out. So we just ordered something to, so that won't, you know, that won't
see.
bother the paint.
That's an interesting problem. Mhm.
Yeah. Yeah, welcome everyone. Good to see you all. We are just going to wait a minute or two before we get started.
Oh, really?
If there are any new people in the group, would be great if you introduce yourself if you haven't attended this meeting before. Okay, I think we will get started because I know you know, there's probably going to be a good discussion on this, so I want to give us enough time. And then all right, so welcome everybody to the ILLIXR Consortium open meetings. Today we have a different type of talk. The talk is on a very exciting simulation platform. I know when we present ILLIXR to architects, one of the questions is, yeah, but how are we going to simulate parts of this workload in an end-to-end context on accelerators that don't exist today? And so Sophia Shao's group has been working on a similar problem in the context of robotics. And we are very fortunate to have Dima and Nikiforov, and I hope I pronounced that right, Dima, and Kris who are students of Sophia's, and also Bora Nikolich's. And they've been working on this problem. I gave a talk at Berkeley, and I was very impressed with Sophia's students. We had a really nice chat about using ILLIXR and what they're doing. So we are hoping to apply these ideas in the context of XR as well. And you know, maybe some of you will pick this up and project, either working with Sophia's group or by yourself. But yeah, that's the context of today's talk. And before I hand it over to Kris, to Dima and Kris, next time we will have Anjul Patne talking about metrics for evaluating image quality, especially if you want to apply technologies like foveated rendering. How do we evaluate image quality? So Anjul is from NVIDIA. He's one of the world's experts in this area. So please join us next time for his talk as well. So let's take it away. Who's going to go first, Dima or Kris?
Yeah.
Oh, and I want to welcome Sophia, of course. I think most people here know Sophia. She's a professor at Berkeley, yeah, leading this project.
And one thing, could you enable screen sharing? I think it's disabled.
Oh, okay. Is that?
Yep, done.
All right.
Okay. Yeah, I can get it started. Hello, everyone. Today, we're going to present on the co-simulation platform that Dima and I has been working on for a long while, which involves system-level pre-silicon evaluation of the robotics SoC. Now, I just want to give a quick introduction of both of us. So, Dima, if you want to take it away.
Yeah, so I'm Dima, so I'm the second year PhD student here at Slice Lab, and I'm kind of in general interested in developing accelerators for robotics and also doing their system integration. And Kris?
Yeah, I'm Kris. I'm a master's student at UC Berkeley, and I'm also interested in hardware software code design, also a graduate student researcher at Slice Lab. Yeah, so just want to give a really quick heads up, given this is the ongoing project, so we definitely expect both side conversation, definitely looking forward to hear the feedbacks and also comments from your side. Yeah, Okay, to get it started, first of all, I want to introduce you to the robotics domain in general, and also want to give a quick introduction to our motivation and the reason that we choose to work on this kind of project. As we saw, nowadays, robotics area has been more and more popular with increasing complex system, which leads to tighter latencies and energy constraints. And a lot of work has been done not only in the industry and also in academia, trying to accelerate those workloads for robotics. And also, robotics involves with a wide range of different tasks and workloads, ranging from dynamic simulation, motion planning and control, optimizations, and also mapping and localization. And nowadays, we saw more and more machine learning stuff and modeling for robotics. Besides the wide range of robotics tasks, all the tasks also involved in the system have a complex interaction, not only on robotic system level, but also on architecture level. Basically, not only inside of this algorithm, inside the SoC, the nodes cannot depend on each other's output, but also depends on the outer side, like interaction, like human interaction, and also the data, the environmental data that we generated from the sensing and actuation. Because of those two reasons, the wide range of workload and also the complex interaction between those workloads, this really requires to focus on one specific part. That's why we choose UAV, which are drones. This is because the unique choices or options for design points basically is due to the constraints that we have been facing in this area. We have seen for drones, we are required really tight deadlines, also requires the low latency so that the drone, when it flies super fast, it doesn't really trying to avoid them. So basically trying to not crash our drones. And also in terms of the energy and power constraints, we want to make sure the drone also when it flies super fast, we want to make sure that the trade-off between the energy efficiency and also the quality of the flight has been maintained along the way. And also given our drone is super light, so every single clamp that we put on the drone is really going to impact the quality of the flight. That's why we focus on lightening and also making sure the weight that we put on the drone doesn't impact the quality of the flight. And also the last part is also the most interesting one, which is the system architecture choices. Basically, thinking about the drone, we could think about how to allocating the computing power onto our drone. Basically, we can carry out the workload on drone, the continuing computer on drone themselves, or on the ground control, which is on the edge, and also even load it to the cloud to finish those workloads. Even though we're focusing on the UAVs, along the way we found there are a lot of overlaps between UAV and also the extended reality that you guys have been working on. Basically, just because both of us are facing this latency constraint. As I know, the latency requirements is super high for the extended reality, so that the user experience will be better. Users don't feel dizzy when they have the wearable devices, and also the energy impact also is really important. Also the weight, given those are wearable devices, we want to make sure the customer have a good experience, which want to kind of having the lighter weight as possible. And also in terms of the system architecture choices, for sure, thinking about the computing resources, should we allocate those to the wearable device themselves or the local laptop or computers, or should that be on the cloud? So those are the common topics that we are facing from both of our groups. So definitely want to discuss this today. Yeah, now let Dima to give you a quick introduction to a deeper detail of this research.
Yeah, so thank you Kris for the introduction. So now I'll go back to talking a bit more on drone, and I'll talk a bit both on what's the kind of software and hardware design space you can see in these drone applications. So first, one interesting observation that was found in kind of some prior research and science-based exploration is that really these drone workloads can be kind of divided into two different areas, where you have an inner loop for your control, and as well as an outer loop. And the inner loop is what really faces the really critical real-time constraints, versus the outer loop has some more decoupling, but also tends to run some of these algorithms that can actually be difficult to accelerate and have really long compute times. So on the inner loop, so this is typically just for really low-level control, and typically would run at a rate of 50 to 500 hertz. And there's no real benefit at this point to accelerate some of these tasks because, again, beyond that update rate, it's the behavior is kind of limited by the drone's physical response. Even if maybe you could, do a PID update at like 10 kilohertz, the drone still has some inertia. There's still the sensing data that comes in at a certain rate. So again, at this point, it's there's not the same benefits. And again, these are kind of really low-level embedded tasks that involve like doing sensor data filtering and like immediate responses to things like turbulence or other disturbances. And the control output here again is kind of low-level output, like the direct output to the electronic speed controllers and such. On the other hand, in order to get true autonomous behavior, you still need an outer level of control that can provide more intelligent behavior. And so this could include things like we saw before with SLAM bench, like the simultaneous localization and mapping, and this is still a huge ongoing research problem, as well as different optimal control and perception. And so it's at this point that would actually have more limitation on things like your flight time through the high power draw for these tasks. And also, as we found in some prior benchmarking work, that accelerating some of these tasks, this is what really can contribute to better quality of flight compared to kind of the lower level loop, which is just more directly interfacing with the sensors and actuators. And kind of looking at kind of what the specific design space is in terms of hardware, again, these two control loops are typically decoupled across the inner loop board, which is typically runs directly on some microcontroller, usually this ST ARM microcontroller. And on the other hand, on the outer loop, this kind of can vary widely. Again, Kris kind of discussed the different design points, like when considering an onboard companion computer. Again, like there are a variety of different available hardware ranging from things like Raspberry Pi to a Jetson board, or even some combination like Intel had an FPGA integrated with their Atom processor. But again, each of these have some still different drawbacks at the moment. On an SoC like Raspberry Pi still can't really support all the different outer loop workloads. And on the other hand, some units like the Jetson still have really high power consumption, so that doesn't really fit the energy requirements. And there has been more research done on using FPGA application, which does seem promising. But again, we can have even more improved performance if we could map these workloads to a custom ASIC. Yeah. So now that we've kind of talked about this background of the design space and drones, I'll talk a little bit about what we see, like what are some opportunities in the space of doing simulation and evaluation of these sort of systems. So the first thing that's interesting is doing more real-time profiling. So a lot of the current benchmarks for these algorithms, for instance, let's look at VIO or SLAM, kind of work on existing recorded data traces, and their evaluation metrics is more focused on factors like the accuracy of the state estimation or the reliability of the system. And even when looking at like the energy, even looking at when the things like energy consumption or latency, it's kind of not really done in the real-time setting. It's just doing measurements on like the latency of such kernels. But the work that has been done is really interesting, but it'd be interesting to see combine like seeing how well just the accuracy of the algorithm is on the data set, instead maybe see, okay, how do we factor in the fact that in the real-time setting you might be dropping frames and have other such effects. Additionally, there's more opportunity to do more SoC level evaluation. A lot of times, like particular accelerators, they evaluate the performance of their particular algorithm on the accelerator in isolation, just looking at input of one node in the system. But as we see, it's really important to capture the co-location contention on real systems, because again, there's so much interaction going on. As in your work in ILLIXR, you presented a lot about how you have these very complicated execution schedules and also all these different software nodes interacting with each other. And it's not if we kind of focus more on the SoC level evaluation, we can have a much more comprehensive picture on the performance of each of these individual nodes, and as well as at the system level, which kind of ties into the last phase, which is like, okay, if we are interested in doing this SoC level evaluation, how do we actually explore like very fine-grained design choices that we're working on? Because currently a lot of the prior work that's been working on like hardware in loop or full system benchmarking in robotics still has to deal with real hardware that exists. And so again, this means that we can't do any pre-silicon evaluation on new hardware, and also kind of rely on existing hardware kind of limits the design space that can be explored, because you can only do tuning on whatever devices you have. But again, I think this last point is especially interesting just because of the kind of result that the past work has shown. So in this diagram is showing a prior benchmarking work, MapBench, which tried to do some system level evaluation of what happens on the quality of flight of a system when you tune different parameters like frequency of number of cores on your hardware. And there are interesting results here that we kind of want to go forward in our infrastructure, where it's not just a simple effect like when accelerating a kernel, it might result in increased energy consumption for computation or reduced latency for that particular node, but there are real quality of flight impact as well. Because for instance, on the left, you see some plot that found in their paper where when you accelerate the workload, you scale the number of cores or scale the frequency, the drone velocity can actually increase dramatically by several factors, going from 0.8 meter seconds to 2.8 meters per second, just because now the drone can react in a shorter deadline and therefore can move at a higher velocity. And so the acceleration has a dramatic impact on this full system level behavior. And this kind of leads to interesting effects where, yeah, even though usually scaling the cores or frequency will increase the energy consumption for the task, in this case, it actually overall for the mission time, it actually results in a decrease, because again, it factors in all the other components of the workload, such as the actual motors and such that contribute to a really high energy cost. So again, there are these interesting system level effects that you find when you try to do this kind of performance evaluation beyond just the individual component level. And this is kind of what we want to explore. So given that we present some of these some of the opportunities in the area, I'll hand off to Kris to also talk about how specific users and researchers can make use of this kind of system. Sorry. Before that, I guess, sorry, one thing is that we still also, I guess the main objective that we want to say is that the end thing we want to deliver is we want to enable robotics researchers to accurately evaluate these heterogeneous robotics SoCs running the full software stack in a real world environment. And so, yeah, to do this, we are presenting the co-simulation infrastructure that, yeah, we'll be able to run these end-to-end robotics workloads, profile the performance on the simulated hardware, and observe the simulated behavior that we mentioned by integrating both RTL simulation as well as an environmental simulator. Yeah, sorry, I'll hand it off to Kris to talk about the target users.
Yeah, that sounds great. So as we now have a better overview of our project and also our motivation and objective, now I would like to introduce you to our three kind of different target users. So basically, as we contributing to this community of software hardware co-design, we identify the following target users from accelerator developers, which are mainly just in our lab, and also the algorithm researchers, software developers, and also the system designers. In terms of the accelerators perspective, right? The accelerator developers perspective, we want to extend the accelerator prototyping flow to support the robotics environment. So previously at our lab, to accelerate the accelerating hardware's flow is basically self-contained onto the SoC. Basically, the typical flow is developer accelerator, generator design, run simulation on the benchmark. But all those are kind of self-contained onto the SoC, and also using pretty pre-limited data trace. To evaluate the performance of the hardware, we really want to not only look into the performance counter, but also trying to see how well it performs on system level. Basically, we want to analyze the system behavior. That kind of requires to look beyond the low-level parameter, but look into the raw behaviors of the drones. So we propose a solution of co-simulate of the chip simulation with the robotics environment using our COSIM infrastructure. This not only allow you to get the low-level parameter that's generated by the performance counter, but also the high-level quality of the flight behavior that you will be able to directly see through this co-simulation. For the algorithm developer side, we also want to provide them the software infrastructure for them to leverage. Basically, as a software developer or algorithm researcher, I want to test my algorithm on the actual hardware configuration and also the application. So our co-simulation infrastructure will allow you to have this one-stop shop of a full stack experience of using our not only to test your algorithm on your application, but also to really test it with actual hardware components that simulated the real world situation. So we also allow you to do pre-silicon evaluation. So even before our new chip RISC-V comes out, you will be able to test it using our co-simulation infrastructure and make sure it works on the raw data when the chip comes out. Yeah, this allows parallel works for sure. And then last but not the least, for the system designers, we also, given we have the hardware configuration that we decide to use and also the software algorithms, which combination will work the best as a whole in general. So that kind of requires our system designers to take a look to really test it out. And our COSIM infrastructure will give you this one-stop shop for testing the different combinations of hardware software to make sure that you found the optimal choices for your algorithm. And now I will let Dima to dive deep to see the co-simulation infrastructure.
So now that we've kind of given the overview of what kind of the problems are and kind of what we want to provide, we'll go into some more specific detail of what we've been developing and all the different components there. So to begin, I'll just go back and give a quick overview of, in general, what the co-simulation infrastructure itself is. So again, our goal was to do this end-to-end evaluation and both be able to analyze the low-level architectural performance as well as the system-level performance. And so to do this, we have three main components. So first, we're building off of two kind of existing infrastructures. First, we are right now, for working at drones, we're building upon AirSim, which is a drone simulator developed by Microsoft. And so this mainly provides us the infrastructure to do the physics simulation of the drone itself, as well as generating sensor data like camera data, provision workloads, as well as all the low-level sensing like IMU data, as well as provide modeling of the actuation that then we can provide from our control outputs. Additionally, since we're mostly interested in looking at the high-level control loop, the AirSim also provides modeling and support for integrating a lower-level flight controller that again handles the low-level control task, versus we still mainly focus on these higher-level algorithms. On the other hand, the other infrastructure that we're using and also modifying and building on top of is FireSim, which is developed here at Berkeley. And so FireSim is RTL simulator for simulating our digital designs, and it still allows for cycle exact simulation while operating at a much more reasonable throughput due to the fact that the RTL simulation is accelerated on FPGAs. And then the particular component that we're adding to integrate these simulators is our synchronizer, which allows us to basically make sure that these two simulators are aligned together and actually produce realistic results. And so as we're working on this, we still have to kind of solve some different challenges to make sure that whatever we do is feasible. So again, we need to make sure that we have synchronization between what's running on the hardware on the FPGA, as well as in the physics modeling environment with AirSim. We also need to make sure that we can have reasonable performance for this simulation, because again, we want these robotics tasks tend to happen on over the order of minutes, and we want to make sure, even though we're simulating the hardware, that we can actually get a decent turnaround time on the results. And finally, we want to make sure that we have a full supporting software infrastructure, because again, we can't do any of the system level work without the software to back it up and be able for users to deploy their particular workloads onto there. And so I'll begin by talking a bit about the synchronization challenge and how we approach this. And so to begin, we just have a synchronizer unit that integrates with both AirSim and then FireSim. And there are two main tasks to do here. The first key task is kind of shown on the bottom here, which is synchronizing the simulation time, which I'll go into in a bit more detail. So in this case, again, we want to make sure that the simulation time seen both in AirSim and FireSim is the same. Neither of them can run ahead without the other, and that they have both the same reference time. Additionally, along with synchronizing the time, we also need to make sure that we enable the data communication between the FPGA hardware and the AirSim simulator, and that we have some kind of translation between the API used in the simulator and the kind of the outputs you would want on your SoC. And as well as we want to make sure that the data is also scheduled in a way that's representative of what would happen in a real system. So again, to go into the kind of the challenges and within the synchronization is first just make the distinction. When we're talking about synchronization, we both talk about real time and simulation time. So real time is just literally the time that's passing in the physical world, and versus simulation time is the unit of time that happens in your modeled environment. So in a lot of cases, especially in robotics profiling, it's done in a hardware and loop setup where you have your actual SoC that you would use in the end application integrated with some simulator. And in this kind of setup, the simulation time and real time are the same, because again, you want to evaluate the true hardware that you're seeing, and it's running in real time, and the simulator has to keep up. But in some more pure simulated environments, there is a distinction between simulation time and real time, because again, the simulator could either run slower or faster than real time. What just makes sense is that the time step that you're looking at is consistent. So for instance, if you're doing your RTL simulation for hardware, your clock cycle within the simulator is the simulation time. So that would correspond to a time in real world, but can have variable execution time when running in simulation. And so like in the ideal case where we only consider simulation time, we have our two different simulators with our physics engine and also our RTL simulation. Each of these have, within the simulated environment, these should have like some corresponding time. So within a certain time that it takes between physics ticks, a certain number of clock cycles should also pass. And in the simulated world, this is always aligned, but the problem starts to happen when you start to execute this in real time. So if you're using, if you're both the physics simulator and your RTL simulation are kind of offline simulators, they're not really meant to tie into any real time. This could result in every tick or clock cycle taking a different time to compute, and pretty rapidly, like these simulators are going to be no longer synchronized. And kind of the black bar represents what should be the same simulation time in the system. But then because of the changes in real time, you're going to have data being passed through at different, not aligned within the simulated world. So that means any behavior observed is going to differ from what happens if you then would try to replay the same scenario in real life.
So Dima, I'm just, maybe this is irrelevant, but I would have expected that the physics ticks would have taken less time. So is there, so can you help my intuition here? So here, the way you show it is each, I don't know what physics ticks mean.
Yeah, so I guess physics ticks here refers to just the within the simulator to be able to compute the next state of the system depending on what inputs you provided to the simulator. So in case it's not just the physics tick, like for doing the the next state of your, for instance, rigid body dynamics in the system, but also be able to do the rendering of your frame for if you're doing generating any sensor input. So I guess in this case, again, this could still take variable time, I guess, depending on if you're, for instance, if you're on your rendering side, you're rendering a simpler scene versus more complicated scene, or on the physics side, if you're handling some like collision events or something, or if there's not much going on. I guess, does that kind of answer the question, or is there?
Yeah, but I would imagine that an RTL simulator would take a fairly long time for each tick, and so, but this is not important. I understand the concept. Yeah, we can.
Yeah, and actually that's a good point, because that's one thing we'll actually talk about in a bit, is like this kind of big distinction between like how many clock cycles you have and like the granularity of the physics tick. Yeah, so but I guess before we go into just like some other simulator kind of like maybe that are meant to be deployed in real-time application, like AirSim, it's initially, it's really designed for a hardware and loop setup, and also like kind of evaluating the different reinforcement learning workloads. So in this case, their approach is instead have like an online simulator, which is expected to give like a fixed update at a fixed interval for different frames. And so in this case, if at one frame it can't really complete the computation, this can result in frame drops, which again would result in your RTL simulation being exposed to older data. And so some of these simulators have some option to kind of scale a physics tick, but again, this doesn't really solve your problem, because even though you can kind of match these two to have the same average throughput, in the end, you're still going to have like real time and simulation time differing at different points. And so really what we want to achieve here is instead to support lockstep synchronization between these two simulators, where at some simulation time granularity, we would install either the RTL simulator or the physics simulator to make sure that the simulation time is always aligned. So we run the simulators for a certain duration, then make sure both are caught up, and then continue execution. But again, kind of as was mentioned, is again we need to consider like some of the numbers here. If we want to simulate this at something like 1 gigahertz SoC, we want to do like update our physics engine at something such as 60 frames per second. This results in having approximately 20 million cycles that we need to calculate per tick. And again, like in a typical, so in this case, typically we'd find that the RTL simulation delay is going to be much longer in most cases than the physics engine. And so this kind of will tie into, we'll discuss this a bit more when we're discussing on why not only do we need to implement the synchronization, we also need to make sure that whatever simulation infrastructure we have is actually feasible and can run the simulation in a reasonable time given this disparity. And so to begin for this, I'll first talk about why we're using FireSim for our RTL simulation in our design. Again,
this is Javier from Excel. Could I ask you a question about the previous figure?
Sure.
Just want to understand. So this periodic interval, you're saying that you define based on an average physics delay that so you're saying 60 frames per second, right? Are you making this interval as wide as 1/60? Just for an example in the next figure.
Yeah, so I think so. This is something that you could still be, that's pretty tunable. We've really worked with some other physics simulator, like the Gazebo simulator for robotics, and so that one would a more typical update rate would be something like 1 kilohertz there. So okay. It kind of, but yeah, depends on like depending on application again what kind of update rate you need for your sensor data and such. Yeah, this is just in this case as an example based on kind of like the default configurations. Yeah.
Okay. Thanks.
Yeah, thank you for the question. Yeah, it's a great point because again, like different domains have different requirements on kind of what kind of sensing they have and what kind of engine you're using. Like in the drone case, I guess you can have coarser granularity, but in more complicated rigid biodynamic system with more complicated system dynamics, yeah, you would use like a higher update rate.
Yeah, so I think if we can just relate it more concretely to ILLIXR. So Javier, so I think maybe the motivation that Dima had for putting 60 frames per second is is the rendering, the vsync interval that we have
Yeah.
in ILLIXR, and that would be, 60 would be a little bit low, so it would be about 120, 140 hertz. That's the default configuration. So, and again, to relate it to ILLIXR, so unlike the AirSim and so on infrastructure, we would actually be doing the rendering in real time, right? It's not a simulation. And so we would have the actual time. But yeah, let's continue. I'm sure there's
So my question will be, what would happen if the physics basically you have this time allotted for the physics and you are not done on time by the end of the 1/120 here, for instance, this particular example. So you would just drop that, or I just want to understand that part.
Yeah. So in this case, that's kind of shown by the physics delay section. So in this case, yeah, because again, we don't, in this case, the real time isn't really, it's just relevant to like how long it takes for us to simulate the whole system. But in terms of like what we're modeling, that's not really relevant. Again, we want to focus on what time step we have in simulation time. So when we're saying, well, if there's a delay in the physics, that physics delay is still, or rendering delay, it's still referring in this case to the same amount of time in the simulated world. And so in this case, yeah, if the physics is taking a normally long time for that iteration, for that frame, we would instead have to stall the RTL simulation until that's being rendered. So again, all of these conclude at the same unit in simulation time. So yeah, we need to support like kind of this
Okay.
stalling on both sides. Yeah.
Yeah. Good. Thanks.
Yeah, and again, because like in the end, like we still, all these timing are purely within the simulated model world because we don't have the real hardware on either end. That's why we kind of have the capability to do this stalling. And so this kind of goes into, so on the AirSim side, that's a bit simpler because again, we have API calls there for like advancing one frame in simulation, so we can step that itself. But then how do we, do that kind of stalling without affecting, the quality of the simulation within our RTL simulation? So in our case, we're building on top of FireSim, which is the FPGA accelerated RTL simulator developed here at Berkeley. And so the overall structure that we have is we have basically the simulator is split up across both on the CPU on a host instance, and as well as stuff that's running on implemented on an FPGA. And so really on the bottom right side where it says target SoC model, that's what's the actual full RTL model of the particular SoC that you're simulating, including all the everything on all the different compute units, the memory, different I/O modules. But again, we need to be able to connect that to the external world. And so in this case, in FireSim, that's handled through different bridges, which kind of provide kind of like a test harness environment from taking the specific like a UART RTL that you might find on your SoC, and then kind of simulating the input and outputs into the actual world. So both these are running on the FPGA. So the bridges just directly run on FPGA clock cycles versus the target SoC is still a model. So the clock cycle on FPGA doesn't correspond with the clock cycle of what you expect on your SoC. Instead, you're going to be to make sure that for instance, some operation might take multiple FPGA cycles to simulate one SoC cycle. So again, this clock rate is kind of different. Also, when handling the simulation of the I/O through these bridges, if there's already support for like doing stalling of your system. If, for instance, you are modeling some block device read from your disk, that still has to use the real physical hard drive on whatever system Amazon instance that this is running on. And so again, you would use a system of tokens and allocating tokens for each clock cycle to be able to stall the SoC model, whereas the FPGA clock cycle keeps going. So in this case, we implemented a similar bridge to interconnect with AirSim, where we have a stall unit that basically both is able to stall the clock of the SoC model and to kind of maintain this deterministic unit of simulation time. And we need then to kind of communicate outward through the towards AirSim, we need to go back to the CPU and software. And so we also write a bridge driver, which can communicate through the FPGA to the bridge on the FPGA through memory mapped registers. And so this is kind of the interface that we have right now. And so at this point, then we can use our co-simulator custom API we wrote to just communicate with our synchronizer, and then that gets translated into API calls within AirSim, such as like setting waypoints or receiving sensor data. I think one important question that we've kind of feedback we've gotten before is also, especially in applications such as even in robotics or going forward to extended reality, like there's a lot of really high throughput data for things like camera data and such. And so down the line, there's support in FireSim for these bridges to also communicate through the PCIe when the FPGA is mounted on the system. We currently don't have that support, but that's one thing we probably want to consider for the future. But again, this would really more of an impact on just the performance of the simulation itself in the end. Again, because we have the capacity to stall, even if it takes longer to transmit data through these MMIO registers, that just affects like the real time of the simulation. But within simulated time on the SoC's perspective, like we can make no clock cycles pass while the data is being transmitted to and from the bridge and the bridge driver. So, and again, kind of what mentioned before is, given this design space, like, is this actually feasible to run RTL simulation in the time we want? And so looking at some example task in a drone application, let's say we want to, there's a drone that needs to do some kind of maneuver and maybe do some scanning or such in an area. And we want to simulate a 3-minute flight with again, an SoC running at 1 gigahertz. And so we can kind of find the time by looking at the task duration times the simulation real time by the task duration times the SoC frequency over the simulation frequency. And so in this case, if we, for instance, look at software RTL simulation using something like VCS or Verilator, like simulating something like a rocket ship might run at 5 kilohertz, 5 kilohertz clock cycle per unit real time. And so in this case, this 3-minute maneuver would take over a year to simulate on our 1 gigahertz SoC. So this is totally not feasible. But if we use FireSim to have the FPGA accelerated simulator, we could run this in 3 hours, given that if the modeled clock time on the FPGA would be something 20 megahertz, which is a value we can achieve. So in this case, yeah, this turns it from like something that's totally not feasible to do to maybe slightly annoying to wait, but actually, reasonable simulation to run. And so based on prior profiling, we found that this synchronization doesn't really impact the overall throughput of the simulator before. So again, so I'll skip to the slide where we talk about the performance when we're doing this on the FPGA accelerated simulator. And so different plots here are like kind of the latency of the physics tick compared to how does that affect, and also how many, like we looked before, how many clock cycles happened before physics tick. So this is with the Gazebo robotics simulator. And in like a typical design points, then here of a 1 kilohertz like physics update frequency and simulation time, we find that this does not really form a bottleneck on the performance of the simulator, given the overall latency needed to update each unit of cycles in the RTL simulation. And so
can you actually walk us through that? So what are these different curves and what, I don't know what to take away from this.
Yeah. So I guess this kind of, it kind of looks like a roofline model, but here the idea is like what's going to be limiting the throughput of our co-simulation infrastructure. So on the x-axis, we have how many clock cycles correspond to 1 physics tick. So this kind of involves both like considering what's the target frequency of our SoC and also the update frequency and simulated time of our physics engine. So for instance, if we want like an update in the physics engine to represent 1 millisecond, and we also know that 1 update of clock cycle in our SoC is going to represent 1 nanosecond if we're running at 1 gigahertz. then in that particular design point of the simulation updates, granularity, and the expected SOC frequency, we have to simulate 1 million cycles per physics engine tick. And so in this case, given like even like in that case, like a 10 millisecond update of the physics for each of those 1 millisecond actual simulation time, we find that the overall simulation throughput of our SoC does not get degraded. It only really gets degraded once we have to kind of be stalling, waiting for the physics engine. When we have to simulate, for instance, something on the very end of the graph, like we have to simulate 1,000 cycles on SoC and then wait for another physics update. But again, like the common design point that we have of like 1 gigahertz or even up to 1 kilohertz update rates won't be really impacting the throughput of the RTL simulation. And again, the 1,000 kilohertz was kind of in the gazebo space, like looking back at 120 FPS or 60 FPS, that's going to result in even more SoC cycles per gazebo tick. So kind of the additional synchronization and integration of the physics engine won't like result in the SoC being stalled even further and reduce the overall throughput of the RTL, which is kind of constraining like how long it takes to run these like cycle exact RTL simulation. Yeah.
So I'm not, when you say synchronization update latency is 40 milliseconds, what is 40 milliseconds? That's a long time, so I don't quite understand what that is.
Yeah, so that's something that when we were working with Gazebo Simulator, we were finding in that case, like, yeah, this is kind of surprising to us as well, like, because yeah, this kind of factored in both the latency of the network communication, because we needed to communicate between different units, one with the FPGA accelerated device and also the GPU accelerator for Gazebo. But also we found that we're still like looking into there on how like also it seemed like when writing plugins for Gazebo, like there was some latency within their internal API as well.
So maybe if you can go back to your block diagram, I'd like to understand what is this latency? Where are you measuring this? What does it capture?
Yeah, so this was kind of captured when in kind of going from the beginning where we're allocating cycles to the FPGA and also allocating one physics step to the Gazebo simulator, and then measuring all the time it takes until we have confirmed that everything we needed is transferred between the two, and we've completed like another step of execution on both simulator. Yeah.
Okay.
So maybe just a follow-up note. So what Dima is trying to show, if we go to the sweep plot, later, it's more like we show like those diagrams, like how frequently we stall, and basically we're adding fences so that we can actually get synchronized, right? So the x-axis here is basically showing how frequently we're actually adding those fences, so things are synchronized. What Dima is trying to show that unless we're just adding fences super frequently, we like to make sure everything is synchronized. You are actually more towards the right part. We're not actually updating or synchronize that frequently. Mostly, we're not really limiting the SoC simulation cycles. We're actually still achieving the maximum throughput. If we're actually doing a lot of synchronization very frequently, there's also overhead associated with those synchronization. So it's more like a trade-off in terms of how accurately we want to do. Do we want to get super fine-grained synchronization, or we can tolerate this kind of coarser-grained synchronization without incurring synchronization costs, but still maintaining very high throughput of the overall simulation system. So that's the trade-off. We're able to explore. Again, maybe some application really want to have like super fine-grained synchronization. We can still support that, but then that may actually limit the entire simulation speed. So there is also a trade-off between simulation speed versus synchronization frequency. We're able to expose to the users.
Okay, there's a question. Actually, no, Kris, did you want to say something? You had your hand up.
No, so basically I was just going to follow up on Sophia's points. I totally felt like that will be the point that we want to bring out here. So even though robotics workloads is kind of different from the extended reality, but this part is especially useful for the robotics like community.
Yeah, and also like this 40 millisecond time kind of building up on is again, this is not within like the latency experience in your simulated environment. Again, like Sophia said, that's just kind of the impacting the throughput of like the performance, how long it takes to run our simulation. Yeah.
And then there's a question on the chat. Kwang Din, do you want to ask yourself? We can barely hear you.
Hi, is it better now?
Yeah.
Okay. Hi, my name is Gualing. I just have a question that since I think the Fire Sim is run on the AWS, which is a cloud FPGA. I'm just wondering how difficult it is to like port it to an Intel FPGA or a Xilinx FPGA. I think for ILLIXR, I think I'm not sure, but I think that would be a good option to have.
Yeah, that's a good question. So yeah, currently like we're simulating like our environment in the cloud environment. Currently there's the FireSim development team is working on also doing working on local FPGAs as well. But currently we haven't kind of used that infrastructure ourselves yet. But yeah, that's one thing that I think down the line could be something that we can support, given that's like a ongoing feature within FireSim. Yeah.
Yeah, I can add a little bit more details there. So FireSim is currently exploring support to local Xilinx boards. So we actually have a couple of Xilinx boards already available, and we are very interested also doing like local prototyping, right? So we're adding like local prototyping support on Xilinx FPGA. So that's something we're already doing. For Intel FPGA, we actually through a different project, we actually also got a couple Altera or Intel FPGA boards. So that's something we're interested. We don't have a lot of experience with Intel FPGA. Most of our students are basically trained with Xilinx FPGA. So we have a couple boards we're interested in exploring that direction, but that probably takes longer, but it's also on our roadmap for that FireSim.
Got it. Thank you.
Sounds good. Yeah, in that case, then I kind of after talking about the FireSim aspect, also kind of to Kris, who can talk a bit more about also the supporting software infrastructure.
Yeah, that sounds great.
So just a quick note, we have roughly 5 minutes, so maybe we need to also probably I think Dima and Kris also prepare a demo in the end, so may want to go this part a little bit faster and then get to the demo. What do you folks think?
Yeah, I just want to quickly get through the user flow also to answer Quan Ling's question. Basically, so to use our co-simulation infrastructure too, first of all, you definitely want to deploy your software onto our co-simulated environment. We provide you a build flow for generating images that you could load onto the SOC generated by Chipyard, and also we provide a set of libraries, the ROS libraries that you it's already ported to RISC-V. So basically, you could leverage the RISC-V infrastructure side to build your applications. And also, like after that step, basically you want to build and run your design. We introduce you to the very virtual, which Dima also introduced you to earlier. You can leverage that to create the Linux image for you to run on FireSim. So moving on, I would like to quickly introduce you to, now we showed you the system level implementation and evaluation from the system level to the hardware level. Now zooming in on the software side, basically we provide supporting software infrastructures on the RISC-V. So basically robotics is a really well established like community. We need to support all the libraries they're using. That's why we are porting all the libraries onto RISC-V for you to use. And those are low-level libraries, but we want to really navigate through to the next slide, which is to show you the example workloads. Basically, now on a higher level, after you have those libraries and infrastructure tools that we provide you, what kind of example application you could be able to carry out? So for example, drone racing, 3D mapping, package delivery, scanning, search and rescue, and also aerial like photography. Those are the classic like robotics workloads that you would like to run. But then I want to introduce you to a more interesting space, which is also the space that currently a lot of researchers have been interested and also looking into. So basically, this is the first-person drone, which give you an immersive experience with the wearable high side of your XR, like the extended reality wearable, and also have other FPV drones. And for the demo purpose, we would like to show you a really simple workload that we carried out using our infrastructure, which is the waypoint tracking. Dima, do you want to kick it off?
Yeah. So can everyone see the screen right now?
Yeah.
Okay, sounds good. I think I need to reconnect a second, but yeah. So basically, in this case, we were just showing a simple example where we want to start running our synchronizer that's being right now stalling our simulation. And then given that we have our synchronizer connected, we also want to then also start executing our RTL simulation in parallel with this. So in this case, we also start running our RTL simulation. So we see that we are now stepping cycles, stepping frames within the AirSim simulator, as well as currently running an RTL simulation as well. So we're keep granting tokens to the RTL simulation, as well as allowing to do time steps within AirSim. And so at the moment, yeah, so we're constantly being transmitting commands to the MMIO, to the control registers that are responsible for installing simulation in the bridge driver, as well as sending commands. So right now we're sending, for instance, like arming command and then takeoff command to the simulator within AirSim. And so we see that the data has been passed through from through our bridge and to the bridge driver and software, and then finally being sent to the simulator. And so again, this is kind of like a simple example just to demonstrate like how basic functionality of the synchronization and data transfer can happen between simulator. And so, yeah, in this case, the main workload is just, we have our SoC, which is just generating a bunch of different waypoints that are then sent to the simulator track, which then the low-level like flight controller model within AirSim is handling that request. So yeah, this is kind of just present like just the core functionality of kind of what the synchronization and data transfer between these two simulator provides.
Mm.
And so like, for instance, in this case, like what's being demoed on the hardware side is this more simple SoC. So in this case, we just have a single in-order rocket chip that's running this task. So
when you're modeling the SoC, everything has to be on the FPGA, or is it possible to have some things on the FPGA and then some things on a real CPU or GPU?
Yeah, so that's a good question. Actually, we have something kind of we can briefly mention in our, I think we have in our appendix for that. So that's something we don't support right now, but could potentially be done in the future. So again, because of the fact that this simulator isn't running real time, if you did want to integrate some other kind of like real hardware device, you need some kind of way to provide either a way to stall that or provide a model. If you want to synchronize like some external like hardware representing some offboard computation, you can have like some kind of model that you integrate with your synchronizer. As well, if you want to simulate maybe some devices that haven't been accelerated, but you have software models of, you can extend that with additional bridges that synchronize your performance model of your algorithm and then what's running on your SoC. Yeah.
Yeah, I still, okay, go ahead, finish.
Oh, no, oh yeah. So yeah, I guess also some.
I should tell. So we are out of our regular time, but several of us who really care about this can hang on and chat with you a bit if you guys have time, Dima, Kris, and Sophia. But I did want to say thank everyone for attending and remind you all that next week we'll have Anju Patne from NVIDIA. He's world's expert on metrics for image quality, foveated rendering, etc. And he'll be giving what promises to be a really interesting talk on image quality metrics, which are a huge source of problem in terms of evaluating XR systems. So we're looking forward to that. And also I should say that we've had a really nice run of very high quality talks. We do have space on the schedule for the week after. So in case anyone here is interested in giving a talk, please let us know. Okay, go ahead, Dima.
Yeah. Thank you very much for hosting us, and great to keep discussion for anyone who's interested. So I guess the kind of concluding remarks I want to say is maybe just talk a bit more like going forward, like what kind of the application to like kind of ILLIXR infrastructure, and what kind of maybe what we have can provide, and what can go both ways is like. So one interesting thing is like one application is that kind of the Shipyard FireSim framework in general just provides like an environment where you can just do agile hardware and software co-design for any accelerated development or hardware development you want to do for the AR application. So again, giving us the capacity to both within Shipyard generate SoC designs, and also make use of the accelerators that we already have, such as Gemini, as well as accelerated simulation of these designs. I think the other component is currently we're working with AirSim as our simulator. But in the end, this is not limited to working with that particular simulator type. As mentioned before, we also like experiment with Gazebo simulator. And in general, we want to present this as a flexible framework for end-to-end evaluation, where we provide this synchronization layer. And as long as you have some kind of API for doing stepping of timing, as well as just APIs for accessing data from within your simulated environment, this kind of overall structure can be applied to a lot of different use cases. And so it's because the main contribution here isn't just integrating with AirSim, but just having the capacity to have some external source influence the timing of your FireSim RTL simulation. And finally, again, given this agile hardware development, it also gives you, within Shipyard, it lets you again generate very interesting heterogeneous designs, allowing you to perform experiments that not only make use of this heterogeneous hardware and making sure they can have good utilization of all the resources, but also make sure that you can co-locate all these different workloads within the same simulation environment, kind of see the impact of all these different algorithms and also different hardware units, and make sure that we capture all the different architectural aspects of resource contention and such when running these co-located workloads. So, and some potential extension. Again, we mainly focus on AirSim with Unreal, but again, if there's any interest, definitely interested to hearing some thoughts of any other simulators or infrastructures that could be integrated within this kind of framework. So yeah, again, thanks for hosting us right now. And if anyone has any remaining question or discussion, we'd be glad to keep going.
Yeah, totally. And also any suggestions to our future implementation or future like collaboration points, like if we bring that up, happy to hear those.
Yeah, no, this is great. Thank you very much, Dima, Kris, and Sophia. There's one question on chat. Let's take that before we go ahead. Abhishek, do you want to ask it?
Oh, hi. I'm Abhishek from University of Bolu. So I'm wondering, like, are you guys also doing like on-chip training? So I have two questions, but the other question follows up if the answer is yes for this question.
Yeah. So for on-chip training, going back to the Gemini project. So yeah, that's currently ongoing research. There's continuing to do development support for being able to do training on the Gemini accelerator by doing all the floating point computation and all the additional operations needed to support that on the systolic array there. Yeah.
Right. So actually, I was wondering when you saw the demo of this drone, so whether you have tested it sort of in real world environment, because we have this one project in the city of Helsinki. It's a large scale project. We have actual sensor actuator deployed all over the city, so which is generating data in the real time. Some of those devices are fit on the public transport, so there's a mobility angle as well. So we also started doing this on-chip training, but we have noticed that it's really susceptible to device variability and the fault. Whenever there's a fault, the model accuracy degrades. So we are looking into how do we enhance the robustness of on-chip training. So I was wondering, do you guys have any thoughts? Because that's the observation coming from our experience. It's very dynamic.
No, that's a great question. That's something we're definitely concerned about because again, we want to like provide like accurate like end-to-end simulation, but again, yeah, like when running on the real device, there's still going to be some differences. So this is still kind of a work in progress, but something Kris and I have been working on is still doing some prototyping on a physical drone that we built. And so yeah, so right now that's still ongoing work, but definitely like that's one thing we want to keep doing in the future is whatever task or workload we run within simulation, we want to compare that to what we're going to observe in the real hardware.
Yeah. So maybe I can provide, as what Dima said, this is something we're also very interested. I can provide a little bit more context with the Gemini project. So we actually have another ongoing project, a little bit different from this one. It's RTML, like real-time machine learning project. And we are very interested in both supporting both on-chip training and inference. So that's why we developed this Gemini infrastructure that can be used to prototype both training and also inference efficient accelerator design. So in that context, we actually also did the chip tape out last year, is actually focusing on how we can better support on-chip training. So on that front, to your question, right, Abhishek, especially thinking about the resilience aspect, you can actually use infrastructure like Gemini. Is publicly available, fully open source, as Dima mentioned, also compatible with the entire RISC-V ecosystem. We also have the Onyx software tool chain there, so you can actually deploy either your PyTorch or TensorFlow models through the Onyx flow and actually get your models running on the hardware. So if there are like new algorithmic optimizations, you're taking an advantage to actually support more resilient like design algorithm, feel free to actually do that kind of prototyping. We can also do some kind of resource duplication on our hardware. We are actually, for example, instantiating this kind of multi-core Gemini system. They can actually run in either the same or what Dima showing here or different application. We could actually do like multiple, everything is programmable. If you are like want to make sure the data is there, and even do actually some checking, making sure the data is actually consistent. We can also modify the DMA unit or augmenting the systolic array or scratch pad there. So a lot of things are actually also tunable in that infrastructure. So we envision that will also be used for some of the robotic application, maybe also in the XR space, but machine learning is also something we're very interested in, and we're developing this infrastructure to enable better software hardware co-design.
Okay, great. Just a quick question. Can you go back to your the block diagram again?
Sure.
So Huzafa already asked the question about we would need to run the CPU, and so we don't. So ILLIXR is not a simulator, right? So ILLIXR is actually a real system, and then the question is, if we want to accelerate parts of it, how do we understand the end-to-end impact, right? With the rest of it being sort of the real system, and then you want to slow that system down to match the simulator speed, etc. So we do need like various components or running, like CPU, GPU, etc. And so that part that you addressed would be very useful to us if we can extend to that. But my question also is about how much of all this is really tied to FireSim, meaning we have a different, FPGA infrastructure, like a simulation, not a simulation. We actually are prototyping, the accelerators that we are building in our own environment. And so, how much of this technology is really tied to FireSim?
Yeah. So that's a good question. So our implementation itself right now is implemented with FireSim, but again, we try to make sure that first, we want to make sure that what we have is still modular. So that's why we kind of separate our system into these different blocks with our synchronizer, as well as what's implemented in FireSim itself. I guess within FireSim, I guess the question is like, what part is FireSim and what part is just like what you're trying to do with, you know, FPGA prototyping. So for instance, even within FireSim, like if we want to do like, for instance, software RTL simulation of the design and shipyard, the part of the build process within FireSim is to produce what's called the Midas level build, which generates kind of an RTL model that that lets you still integrate these external bridges that can do stalling of your SoC. So in that case, like if you have that RTL, like that's not something you necessarily need to port just to what's in the, you already have that RTL that's generated from that process from Chisel and Shipyard. And at that point, that's could be mapped to, just put that into generate AGFI for, you know, running that in the cloud infrastructure as usual, FireSim. But also like you could be going into a different direction for, like instead take that RTL and put it onto local FPGA, like what Sophia mentioned, with both for like the simulation, but also more in a prototyping context, where instead the clock we see on FPGA, instead of being like the simulated clock, it's more of like a real-time clock that you would expect as if you run FPGA implementation. But I guess the core component here is, again, we still need to, as long as we have like some core component, like in this diagram, like that kind of does what the bridge is doing, some IP that can basically stall your simulation, and you have some way to access that through different methods, like such as through other MIO registers or other IO devices on your FPGA. I think that's, it definitely needs to, like our particular implementation is still, using FireSim, but I think this general approach like is still flexible to try to apply to different implementation and infrastructures. I guess.
Okay, Zishan.
Hi. Thanks for this great presentations. So I'm Zishan from Georgia Tech and Harvard, and I have two these questions. One is that you mentioned like you do this code simulations and can build some agile hardware design. So I was wondering, like when you want to build this hardware, like you're considering this workload algorithm and also the architecture. How do you think this different type of drones with physical components will impact hardware design on that? Because I see like you use this ASPLOS paper, last ASPLOS as motivation. I remember in that paper they say like these different drones have a different weight and have some very severe implications on its final performance. So I'm just curious, do you think or is it better to consider some of the physical components in this hardware design?
Yeah, that's a good question. That paper definitely is very interesting, and kind of give us the importance of being able to select different design points. So kind of looking at kind of they had the plots of showing the different weight of the SoCs or different and how that can impact the quality of flight metric, like the flight time and such. So I think within that agile hardware software co-design flow, that will kind of impact on maybe some broader constraint, like what kind of area we can expect to have, or what is the constraint on the energy consumption for a task or overall power consumption of our chip. So that kind of would, within chipyard and such, that would kind of determine what kind of range of design we want to target. At that point, it's still kind of more manual effort to kind of, based on what we have available, what kind of algorithm we could port onto there. I guess in terms of also the infrastructure itself, if we want to get those kind of measurements and see plug in, make another data point into there based on weight of the drone and the SoC we generate, we can continue to do a physical, do the physical design for SoC. Once we, instead of deploying to FireSim, we use the tool in our lab, Hammer, to generate a layout of our design, do based on a smaller benchmark, do like a power analysis, and then kind of at that point we would have like a power report as well as error report that we can use to estimate those other parameters within that space. Yeah, if that kind of answers your question.
Yeah, thanks. And also have another question. Like, I remember like you mentioned like you map based a ROS system on the FPGA, or like use the code simulation based on ROS. So I'm curious, like, do you face any like difficulties like in mapping the ROS on the FPGA? What do you think is the like some like acceleration opportunities in like accelerated like intra-ROS or the inter-ROS system?
Yeah, I could quickly just answer that question because I was in charge of porting all the ROS libraries to our RISC-V environment, right? Like basically there are like certain roadblocks that I have been encountering. Like most of the times, basically, because previously ROS support all the libraries is kind of like just directly import them will be straightforward, but porting them to the RISC-V, we sometimes need to leverage some middleware like MobROS. We need to leverage the MobLink. Like MobLink need to leverage the MobROS to kind of like as a middleware to be carried out to RISC-V. So there are like certain obstacles. That's also why like it's a long procedure that it's also ongoing procedure for us supporting all the libraries so that we can support the robotics community with all the library they want to use. So definitely there are opportunities of accelerating that procedure and try to support more dynamic, like different kind of like ROS library so that we can support more complex advanced features. Yeah, hope that answered your question.
Yeah, thanks.
Yeah. I guess to follow up that as well. Yeah, like again, the interesting part as well is like, yeah, once we have ported all these libraries to RISC-V, right now so far we're still like importing in terms of like the software itself, so still running on CPU. But again, like kind of once we have more like that more established, like yeah, the interesting question is, yeah, now within those ROS library, how do we map that to like different accelerators? So I guess there has been some infrastructure done in our lab so far, not just for accelerating like machine learning, but just using like our existing accelerator like Gemini from just in more general purpose computing or scientific computing. But in that case, there's some library, like there's been work on doing mapping like a BLOS-like library Bliss to Gemini. So in that case, like something like that could be interesting to look in the future. Like, yeah, like if a lot of these like robotics libraries and ROS are making these calls to linear algebra, like to further build upon that and kind of replace like when we're including like the BLOS library as such, make one that include the one that is pointing to like Gemini rather than purely software configuration.
Yeah. So basically from both software side and hardware side, we're trying to accelerate this.
Yeah, so unfortunately, I have to wrap up. I have a class to teach. So I don't know from the ILLIXR standpoint, what is the appropriate direction that.
So I actually had a question related to that. I think should be a quick question. So I can imagine that in your synchronizer, so there's an API that interfaces with AirSim, and then similarly something that interfaces with FireSim. If you exclude those two interfaces, is the rest of the synchronizer generic? What language is it implemented in? Could we pluck that part out, let's say, and plug it in somewhere else?
Yeah, definitely. I could also just quickly answer your question. Basically, I implement the synchronizer. That's also one motivation of us, like making the synchronizer separated from the rest of the system, basically just to make it generic for different kind of systems to use. So basically only the API calls are directly related to AirSim. So for the rest of the parts, like the synchronizer and the data transformation, those two aspects, basically we implement that in either Python and C++. So basically you could still leverage the basic infrastructure for like other program besides AirSim. So Dima, do you have anything to add upon that?
Yeah, I think maybe that's something maybe get some feedback or thoughts on, is just like kind of if you wanted to use like synchronize like this, what kind of like what kind of APIs would you be interested in such? Because yeah, right now, yeah, well, this is kind of separate unit we could plug into other devices, other infrastructures. For now, it's kind of still kind of based on what we've seen in yeah. So I guess what are some interests?
Yeah, so because my question was, so we have this feature in development in ILLIXR in which we're basically moving away from each of the individual components running on their own clock to a global clock, so a common shared clock. And one sort of straightforward way that I could see of porting this technology to ILLIXR is to just take the synchronizer and implement it inside ILLIXR, right? Forget about whether something is a simulation or fire sim or air sim, but just for the components inside ILLIXR, right? I think if we can drive them and synchronize them using your synchronizer, then I could see how we could then move from that to then an FPGA or a GPU or whatever else that we would like to simulate.
Yeah, that's a very good comment. Yeah, I think looking forward, we can maybe do some thought instead of considering the synchronizer between these two components, maybe a synchronizer between whatever n agents you have that are.
Exactly, right. And then it's a sort of easy case because everything is running in real time on some real hardware. Once you get that running, then you can start abstracting away. Okay, now this is no longer on real hardware; it's on simulated hardware. But so that to me is the main attraction of your design, right? The synchronizer. Just how do you manage these very disparate clocks, and how do you make sure that everybody has the same world view of time, right? What is time, basically?
Yeah, I think that's great feedback. Yeah, I think given that, I think we can probably do some thought and refactor how we're doing the approach. So it can be even more generic and kind of figure out what the API call will be in that kind of environment. So I guess
Right.
we'll definitely be interested in discussing in the future to sit down and have a talk on what the different how in more detail what that kind of would look like.
Yeah, absolutely.
Okay, so are there other questions? I have to drop out, but you all can continue. There's no reason for people to not continue, but I don't know, how do we orchestrate the next step for this? I don't know, Sophia, maybe you and I should have an offline kind of thing as to what extent we want to devote resources to this. I think from our point of view, if we can get something like this working with ILLIXR, that would be pretty awesome. I mean, it will be an enabler for a lot of research for the community.
Yeah, definitely. I'll reach out. I think there are a lot of opportunities, as Dima and Kris mentioned. When we designed this, we did actually try to make it generic. We started with some infrastructure, but really trying to see how we can bridge this different environment, software environment, hardware environment, or real environment, right? So many different things, and we really make sure they are kind of consistent so that we give a consistent view to both hardware and software developers. So that's really the real motivation. We're pretty happy with the AirSim APIs, but now since we're almost done with that, we're looking forward to see how this can be extended. So ILLIXR could be a really fun platform to think about.
Okay, great. I gotta go. So thank you again so much, Kris and Dima and Sophia.
Yeah, I just noticed Tian Yi has a question on the chat.
Okay, I'll leave, Josefa. You can manage.
Yeah, sounds good. See you later.
Okay.
Yeah, sounds good.
Yeah, I also have a visitor in my office now, so I also need to leave, but I'll sync up with you folks later. Thank you.
Yeah, thank you, Sophia.
Thank you. Hi, Dima. I have a very quick question. You have mentioned in the page 6, a metric, I think it's a user level metric. It's called quality of flight. How to define the quality of flight, and do we need to associate the microarchitecture level metrics with quality of flight, and or how to associate the microarchitecture level metrics with the quality of flight? You have here.
Yeah, I think that's a great question. So I guess in general, quality of flight is still something that's, I think, kind of different meaning in different contexts. I think the MAV bench paper, some particular benchmark that we're looking at is high level concept like mission time or velocity. But in general, I think that really depends on your application and as a system designer, what requirements you define for that application. So it's basically, whatever requirements you have for your task, how well does it, meet those? That could range from things like velocity here, but if you have an application like a package delivery, they also can include things like the accuracy of how well it is able to like pick up and put the package in the desired state. As for like tying into a microarchitecture, that's kind of the outcome that we want to kind of explore. And now that we have this infrastructure, we can do some more benchmarking with finer granularity. Like previously already, like in the motivating paper here, we mentioned from S+, like some of the interesting findings there were, again, like when co-locating some like of these tasks, like for instance the flight control firmware as well as the SLAM workload, again, that kind of results in some microarchitectural effects, like more TLB misses when running your inner loop control workload on the same device. So I think, yeah, that's kind of what we're interested to kind of explore and do more measurements and kind of correlate like what low-level like performance counter measurements we get from FireSim side, as well as these quality of flight metrics that the system designer implement that kind of defines based on the application.
Mm-hmm.
Yeah.
Okay, thank you.
Yep.
Yeah,
Okay, we have no more questions. Thank you once again, Kris and Dima, and I guess we'll be in touch. Let's definitely discuss this more.
Yeah, that sounds great. We could also quickly put our email into the chat. So any follow-up questions, feel free to just throw an email. We're happy to connect.
Yeah. Yeah, again, thank you so much for hosting.
Yeah.
Thank you.
Awesome. See you guys.
Yep, see you.
Okay, bye.
See you.